Good morning, everybody. Today, let us start the second program in Power System Simulation Laboratory, which is Power Angle Curve for Salient and Non-Salient Pole Synchronous Machine. So first, let us understand the background theory before going into the program. So for that, we need to understand the definition of stability. Stability is nothing but ability of a system to return to its normal operating condition after being subjected to a disturbance. Ability of a system to return to its normal operating condition. Normal operating condition in the sense the system has to be in operating under nominal frequency of 50 hertz and nominal voltage 3-phase 440 has to be maintained, and the machines running in parallel must be in synchronism. They all must be running under common speed. So this is referred to as normal operating condition, that is nominal frequency, nominal voltage, and then synchronism. And then it says that ability of a system to return to its normal operating condition after being subjected to a disturbance. So disturbance may be changes in load and generation, changes in the network, short circuit fault, or outage of equipment. Load and generation changes in the sense sometimes there may be an increase in the load depending on the consumer, or there may be a decrease in the sudden decrease in the load, or there may be an increase in the generation, there may be a decrease in the power generating sources available. So this is one source of disturbance. The other source is network changes. Network changes in the sense the one of the transmission line that is transmitting the power may fail, so the power will be rerouted through another transmission line network. So there is a change in the network. Then the other possibility is short circuit fault. So you very well know about short circuit fault. In case there is a short circuit fault also, the system stability is hampered. Then equipment outage. Failure of any equipment is termed as equipment outage. So all these come under disturbances. So in spite of these disturbances, system should be able to return to its normal operating condition after suffering the disturbance. Then the system is said to be stable. If it is unable to return to its normal operating condition, then it is said to be unstable. Then coming to the stability, stability basically depends on nature of disturbance, size of the disturbance, and then the time span, applicable time span. Nature of disturbance in the sense whether the system will be able to regain stability or not will depend on the type of disturbance among the four: load and generation changes, network changes, short circuit fault, equipment outage. In each of these different disturbances, the behavior of the system will be different. So then the second dependency factor is size of disturbance, whether the disturbance is of small magnitude or large magnitude. For simple example, whenever a tree branch falls on a transmission line, whenever there is a heavy wind, it might lean on the transmission line, and then once the forcing function wind is absent, it might the tree branch may go back to its original position. That can be considered as a small magnitude disturbance. Then coming to the large magnitude disturbance, there may be a breakage of a transmission line or transmission line pole or tower. That's a huge disturbance. So that is nothing but size of the disturbance. Then coming to the time span, how long the disturbance persists also decides the stability. So the dependency factors on stability are nature of disturbance, size, and time span. Now if you categorize the stability problem, it can be classified into rotor angle stability, frequency stability, and voltage stability. This particular program is based on rotor angle stability. So let us see what is rotor angle stability. However, in theory in the last semester you have already gone through frequency stability and voltage stability. Of course, you will be studying again these concepts in detail in your 8th semester. So coming to rotor angle stability, in order to understand the rotor angle stability, consider a simple example as shown here. It consists of a 5-bus power system network, bus 1, bus 2, bus 3, bus 4, and bus 5, as you can see here. And along with that, you are having the interconnected transmission network connecting these buses. L1, L2, L3, L4, and L5 are the 5 transmission lines. And you can see generators are connected at bus 1, bus 2, and bus 3. And load is present at bus 3, bus 4 and bus 5. Since you already know the single line diagram notations, you can identify the load, bus, generator, etc. So now let us assume there is a short circuit fault in bus 1. There may be a short circuit fault in bus 1. So whenever there is a short circuit, you very well know that the voltage will become 0. So voltage at bus 1 will now become 0 because of the short circuit. So once the voltage becomes 0, let us consider an equation here which relates the voltage and power. On the right side you can see P is equal to EV by X sine delta. So let us later on see what is this delta. Then why we are using this formula, we'll see that later. So in this particular case, now what has happened is voltage has become 0 because of the short circuit. ISC is nothing but short circuit shown on the diagram. Since voltage has become 0, obviously if you take this particular equation, EV by X sine delta, power is also 0 because V is 0, power is also 0. This power is nothing but electrical power output. But since you are having a generator connected to this particular bus, output electrical power has become 0, but input mechanical power still exists. Input mechanical power is provided by the turbine, that still exists, but the output electrical power is 0 because of the short circuit. Because of the short circuit, voltage has become 0, hence power has become 0. Only input mechanical power exists right now. So this is causing a disturbance. So let us try to understand what disturbance it is causing. It is basically causing load disturbance. Your input mechanical power is available, but output electrical power is becoming 0. This is as good as drastic reduction in load demand, because this particular generator is unable to cater the requirements of the load at bus 3, bus 4 and bus 5 because its output electrical power is 0. It is as good as reduction in load demand. So whenever there is a reduction in load demand, obviously the speed of this generator increases. Speed and frequency are directly proportional parameters, so obviously the frequency also shoots up. So whenever the system was stable earlier, the generator connected at bus 1, bus 2 and bus 3 were in synchronism. They were running at a common speed. Now because of this disturbance, there is an increase in the speed of this machine or generator connected at bus 1. Since there is an increase in the speed of this machine, it has lost synchronism among the other two generators. So now the generator connected at bus 3 and bus 2 are running at a different common speed, while bus 1 is running at a different speed. Now bus 1 is racing or accelerated, you can say. Bus 1 is running at a higher speed compared to bus 2 and bus 3 generators. So there is a drastic increase in the speed of this generator. So just have a look at this curve which represents delta versus T. Delta is nothing but called as rotor angle, a plot of rotor angle versus time. Just now I told you the generator at bus 1 starts accelerating, or it goes beyond the generators connected at bus 2 and bus 3. So that acceleration can be expressed as d square delta by dt square. If d square delta by dt square is the acceleration, d delta by dt will be the velocity, and delta will be the corresponding rotor angle. So that rotor angle versus time has been plotted here, and you can see the increase in speed of the machine is indicated here. Delta basically refers to change in position with respect to the reference axis as well as the rotating magnetic field axis. So here this delta is being shown. So delta goes on increasing as and when there is an instability in the system. So since there is a reduction in load demand, delta goes on increasing. So there are three possibilities here. The first possibility is you can see the a sinusoidal curve sort of a thing, where from the initial point the curve goes on increasing, and after reaching certain peak again it goes down, and finally there is a second wave which will again increase and decrease, and this way it will settle down. So you can see three curves here. Depending upon the time taken to resolve the fault, the response of the system will change. Let us assume T1, T2 and T3 are three instances where the fault is getting cleared. Let us assume this fault, whatever has happened, short circuit fault, whatever has happened here, gets cleared at time instant T1 itself. If it gets cleared at T1 itself, the curve, as you can see here, shoots up, goes to the maximum, again decreases, goes below x-axis, again increases, and this is how the pattern will continue, and finally at some point of time it will settle down. Then the second possibility is fault being cleared at time t2 instant. Whenever the fault is cleared at t2 instant, you can see the curve, there is a loss of synchronism. This is the second curve. As you can see, I'm showing in the mouse pointer. This indicates loss of synchronism with respect to other machines. Third possibility, if you are trying to clear the fault at time instant t3, then completely it loses stability and you can see a straight line. So it goes racing and the system is uncontrollable. And since the speed is uncontrollable over here, the system frequency is hampered. So there is a drastic reduction in, there is a drastic increase in the system frequency since there is an increase in speed. So this is the concept of rotor angle stability, and this rotor angle stability right now we'll be seeing for this particular curve. What you're seeing here, delta versus t, is called as power angle curve, and this power angle curve will be plotted for both synchronous machines as well as salient pole machine and non-salient pole machine. You very well know in your machines you have studied what is a salient pole machine, what is a non-salient pole machine. The behavior will be quite different. You'll be studying it here. So now just observe the equivalent circuit shown in this slide. You are having a generator and then equivalent reactance, internal reactance XS is shown, terminal voltage VT is shown. You very well know that always the terminal voltage will be quite less than the generated voltage EG because of the drop in this reactance XS. Now there are some variables XD and XQ. XD represents direct axis reactance. XQ represents quadrature axis reactance. XS is nothing but synchronous reactance. When we move on to salient pole, we'll understand what is XD, XQ. As of now, in this particular case, XS, XD, XQ are equal. I'll explain later on what is XD and XQ. Now, if you just try to write the expression for VT, terminal voltage, it is given by EG minus JIXS because there is a drop in voltage in the internal reactance. Then from this, if you try to write the expression for current I, it will be equal to EG minus VT divided by JXS. Now I want to write the expression for real power P, which is nothing but real of VI conjugate. VI conjugate basically represents the complex power. I'm just taking the real component of that because I need real power. So RE of V into, in place of I am going to use this expression that I've got here and expressing it in polar form, EG at an angle delta minus VT divided by JXS conjugate. So if you take the conjugate, in the next step you can see EG at an angle minus delta minus VT, VT will be at an angle 0 itself, divided by XS at an angle minus 90 since you have taken the conjugate. So this, in the next step you have, if you try to simplify this, you get V magnitude of V magnitude of E cos of 90 minus delta divided by XS minus magnitude of V whole square cos 90 divided by XS. You very well know that cos 90 is 0, so the second term turns out to be 0. You'll be left out with VE by XS sin delta. This is the expression for real power, and this is the expression we have used here in order to analyze in the previous slide. See, in the previous slide I'm showing P is equal to EV by X sin delta. I had told you how this expression has been taken right now. So this is how we got the expression for P. And here you are trying to plot this P versus delta. Delta versus time. The variation of delta versus time we have seen in the previous slide. In this particular slide, you are seeing the curve of P versus delta. This is the power angle diagram of synchronous machine. The other one was called as transition diagram. I had referred to it as power angle curve, but that was transition state. So this is actually the power angle curve of synchronous machine, which is representing P versus delta. So you can clearly observe that in this expression, P is equal to V by XS sin delta. So the variation of P and delta, it's a sinusoidal curve. Whenever delta happens to be 0, sin 0 is 0. So you can see P is also 0. initially in this curve at the lower left corner it is 0, and this power can be maximum whenever delta is 90 because sine 90 is 1. So at this point peak of the curve it will be v by xs, and again whenever delta happens to be 180, power will be 0. So that is being shown here at 180 degrees power is becoming 0. So this is the power angle curve for non-salient pole synchronous machine. Next, we go for salient pole synchronous machine. Anyway, I'm not going to explain this vector diagram right now because already it has been covered in the last semester power system analysis subject. Let us just recall the expression for power. So here you're coming across two components, quadrature axis component and direct axis component, which I was referring to. So quadrature axis component comes into picture whenever you're dealing with reactive power, that is magnetizing component of current. Direct axis component refers to the real axis, or say core component of current. This is with respect to core component of current. So from the vector diagram, the actual P will be a resultant of quadrature axis component plus direct axis component. Expression for P is V cos delta into IQ. So V cos delta into IQ, you can see here. Power is generally given by voltage into current into corresponding power factor. So V into IQ into cos delta plus power in the direct axis component will be V into ID into sin delta. So in the direct axis component over here in the vector diagram, current into voltage into sin delta. This is what you can see here. Then in the next step you can see V cos delta. In place of IQ, I'm going to write it as V sin delta by XQ. So I'm trying to express IQ. IQ is nothing but, see from the diagram you can see IQ is nothing but the over here okay. So here sorry, there was a disturbance in the network. So IQ can be expressed as V sin delta divided by XQ, and then here ID can be expressed as E minus V cos delta by XD. So you can clearly see on the left side it is written IQ XQ is same as V sin delta from the network. V sin delta is same as IQ XQ. So ID XD will be E minus V into cos delta. So I'm just using that here. Then you have the first term in the next step, V cos delta V sin delta by XQ plus V sin delta E by XD minus V sin delta V cos delta by XD. In the next step you have V sin delta E divided by XD plus the other terms left over, V square sin delta cos delta into 1 over XQ minus 1 over XD. If you simplify this, you have V sin delta by XD plus V square into XD minus XQ twice XD XQ multiplied by sin 2 delta. So from the vector diagram, we have substituted for ID and IQ. So if you want to understand that clearly, once again, you can just see this particular vector is basically IQ. And then you are having V sin delta. This part is V sin delta. And here is your angle delta. If you take this particular triangle, this happens to be XQ. Yeah, from the first formula itself you can understand IQ XQ is equal to V sin delta. So in place of IQ I can write V sin delta divided by XQ. Similarly, IDXD is nothing but E minus V cos delta from the vector diagram. From there, I can substitute for ID. So this is what we have done in the second step. So in place of ID and IQ, I have expressed in terms of delta. So that was being done. And finally, after simplification, in the last step, I'm getting V sin delta by XD plus V square into XD minus XQ by twice XD XQ into sin 2 delta. Now, let us realize the same in the program. This is the first one. The first part of the program is for non-salient pole synchronous machine. Our intention here is to determine excitation EMF, regulation, peak power, power angle. We are plotting the power angle curve for non-salient pole synchronous machine. So the first step here, as you know, if you use the prefix as percentage, it is a comment. It will not be executed. First line is P is equal to input enter the synchronous machine power in per unit. From the given data in the problem, you will be getting the synchronous machine power in per unit. That is nothing but P. V is nothing but input terminal voltage of the synchronous machine in per unit. We are asking to input the terminal voltage, and then PF is equal to enter the power factor input enter the PF of synchronous machine. The synchronous machine power factor will be entered here. XS input enter the reactance of synchronous machine in per unit. Internal reactance of the machine XS will be taken as input here from the problem. So we are taking the input of PV, PF and XS. Then you know the formula, I is nothing but P divided by V into power factor, because P is nothing but VI cos phi. Same thing is been done here. I will be equal to P divided by V into cos phi. In place of cos phi I have used PF, and for current I have used IM here. Then in the next step, I am trying to calculate the power factor angle PFA, which is equal to A cos of PF. A cos of PF means cos inverse of PF. Then I am trying to express current in the complex form, rectangular form. So I will be equal to IM cos of PFA minus J sin of PFA. So IM into cos theta minus J sin theta in general, if you consider. So it will be cos of PFA minus J sin of PFA. Then as per the formula, terminal voltage relationship between terminal voltage as well as the generated voltage, E will be equal to V plus JI into XS. Let us go back to the previous slide. So here you can see the relationship between terminal voltage and generated voltage. Vt is equal to Eg minus JIXS. So the same thing is been used here. E is equal to V plus JI into XS. Then excitation EMF, whatever we have to find, is nothing but magnitude of this E. Magnitude in MATLAB is you will be getting it by taking absolute function ABS of E. Then in the next step, the next few steps are for plotting. Whenever you have to plot any curve, already you have seen how to plot curves in your control system lab in the previous semester. So here generally whenever you want to plot any curve, first you will have to define the x-axis variable, then y-axis variable, then you will be using the plot function. So delta is a variable which will start from 0 in steps of 0.1 up to 180 degrees. Then in the next step, I'm converting delta into radians. Delta in radians will be equal to delta into pi by 180. And in the next step, I'll be using the formula P will be equal to absolute of E, absolute of V, sine of delta radian by XS. This is nothing but your EV by XS sine delta. This is the expression for real power for non-salient pole machine. I'll just show you the same. So in non-salient pole machine, at the end, you're getting P is equal to V by XS sine delta. Same formula, I'm using it there. So P will be equal to absolute of E, absolute of V, sine of delta radian by XS. Then regulation is given by E minus V by V into 100. I'm taking the magnitude, so absolute of E minus absolute of V divided by absolute of V into 100, which is nothing but E minus V by V into 100. Peak power, you can get the peak power from the curve as maximum of P. If you use the max function, you will be getting the peak power. Maximum, I need maximum of P. Next few steps, we'll continue with the plotting. Now I'm going to use the plot variable, plot of x-axis variable, comma y-axis variable with suitable attributes. What is that attribute? I need dash R. Dash R means dash represents, I need a dotted line, R represents red color. So I need this particular curve with a dotted line and red color. Delta is nothing but your x-axis variable, p is y-axis variable, and the last part dash r represents the attributes. So it is going to plot delta versus p, or if you conventionally take y-axis variable versus x-axis variable, which is p versus delta, which is the power angle curve. Then I'm going to define the title for the curve, power angle diagram for synchronous machine. Then X label. I need a label for X axis as well as Y axis. X label delta in degrees, Y label three phase power in per unit. Then finally I'm going to print some results. I need fprintf, percentage regulation of the synchronous machine in percentage. So I need to print the regulation. Fprintf, excitation EMF of the synchronous machine in percentage g, which is representing an integer, and then fprintf, peak power of synchronous machine. So I am going to print regulation, EMF, excitation EMF, and peak power, and finally legend, non-salient power. So already you know about legend, I don't have to speak about it. So that finishes the program on non-salient pole synchronous machine. The second half of the experiment is program on salient pole synchronous machine. As usual, we start with P is equal to input, enter the synchronous machine power in per unit. I'm going to accept the input power. Then I'm going to accept the terminal voltage of the synchronous machine. V is equal to input, enter the terminal voltage of synchronous machine in per unit. Third line, PF is equal to input, enter the PF of synchronous machine. I'm accepting power factor from the problem. Here, in the, if you compare the previous program, there you're just taking the input of XS, but here in salient pole machine you take both XD and XQ. XD input, enter the direct axis reactance of the synchronous machine. XQ, enter the quadrature axis reactance of the synchronous machine in per unit. Then see, these steps are almost the same as you can see in the previous case. Im is equal to P by V into PF, where I'm trying to calculate current when power and voltage and power factor are known. So P is equal to VI cos phi. Same thing I'm using here to get the current. Then PFA is A cos of PF, which is cos inverse of power factor to get the angle. I'm expressing the current in rectangular form. Im cos of PFA minus J sin of PFA, as we did it in the previous case. Then here I'm trying to write the expression for E in terms of terminal voltage, relationship between terminal voltage and generated EMF. But I'm going to use Q as a subscript here, because here we come across both direct axis as well as quadrature axis. So EQ will be equal to V plus J into I into XQ, which is nothing but the relationship between terminal voltage and generated EMF. Then you have ID. ID is nothing but given by absolute of I sine of angle of EQ minus angle of I. This again is obtained from the vector diagram. ID is given by, so you can see from the vector diagram, I'm going to get the expression for ID. So that ID is nothing but absolute of I into sine of angle of EQ minus angle of I. Then I'm going to write the expression for E, which is equal to EQ plus ID into XD minus XQ. Again, this is from the vector diagram. Excitation EMF will be absolute of E, that is magnitude of E. Then as usual we go for calculation of regulation, peak power, and plot the power angle curve. Again, delta will be on x-axis. It will start from 0 up to 180 degrees in steps of 0.1. Delta will be converted into radians. Delta in radians will be delta into pi by 180. See, here we try to calculate P1 and P2. One for direct axis, the other one for quadrature axis. So before seeing this line P1 and P2, let us go back to the formula that we have got, then we can understand this. Here you can see the actual power P, real power P, will be equal to VE sin delta by XD plus V square into XD minus XQ by twice XD XQ sin 2 delta. So I'm having two terms here for power. One you can call it as P1, the other one you can call it as P2. Whatever expressions you are seeing here, same thing is written in the standard format in MATLAB. So V by XD sin delta is 1. The other one is V square XD minus XQ by 2 XD XQ sin 2 delta. Let us see them here. You can see P1 is absolute of E, absolute of V, sin of delta by XD, which is EV by XD sin delta, the first term. Second term, V square into xd minus xq, sine of 2 into delta in radians divided by twice xd xq. So resultant of P1 and P2 will be your actual real power. So P will be equal to P1 plus P2. Then as usual, formula for regulation, E minus V by V into 100, peak power maximum of P. Now here, next comes the plotting process. I am trying to plot P1, P2 and P with respect to a common x-axis delta. I'm going to use another function called hold on here because all the curves must be retained. Otherwise, if I don't use hold on function, only the latest curve will be retained and it will be plotted. So delta P1 versus delta. Delta is x-axis variable, P1 is y-axis variable, and K is an attribute. Similarly, delta P2 M. On x-axis you have delta, y-axis you are having P2, attribute is M. Third one, delta PC. X-axis variable is delta, y-axis variable is P. This is a curve of P versus delta, attribute is C. Then finally, the formalities, you're going to give the title for your curve, X label, Y label, and you're going to print regulation, excitation EMF, peak power, and then finally you're going to name legend. And naming will be done, non-salient power, reluctance power, and then resultant power. So this finishes experiment number 2, which is power angle curve for salient and non-salient pole synchronous machine.